In today's lecture, we're going to learn about short column design using interaction diagram charts. And before we do that, I want to remind you of some basic things that you always need to check when you are designing the cross-section of a reinforced concrete column. Here we have what we call a checklist, and I want to go over these things. First off, we need to consider a variety of different types of spacings that need to be achieved to follow what ACI code requires. For instance, we have to satisfy the clear cover requirements. And if you look in ACI 7.7, you will see what the clear cover requirements are. So don't forget about that. Also, we have to make certain that the spacing, that is the clear spacing between longitudinal bars, we have to make certain that that has been satisfied as well, and you can see the rules for that in the code ACI 7.6.3. The next thing that we need to do is also be sure that our hoops or our ties are spaced correctly, and that in fact we also have satisfied the appropriate tie requirements. And you can look for the information in the code for that in ACI 7.10.5. And lastly, there are some reinforcement limits for columns, and these reinforcement limits are basically the limits for rho sub G, which is the gross steel ratio for a reinforced concrete column, and that is found in ACI 10.9. With that information in hand, we are now ready to do an example where we will make use of some interaction diagram charts to design a short column cross-section. So the basic idea here is we are given a problem, and the statement is that we want to design a reinforced concrete column given the following information. We have f sub c prime equal to 4 ksi, f sub y equal to 60 ksi, and we in this problem are given our factored loads. We have p sub u satisfied and m sub u provided also, and we need to be able to satisfy both of these requirements with the design of our reinforced concrete column. Now, you, of course, would have to find these values ordinarily in the course of a design. You might get that by doing a structural analysis using RISA, or it might be that you're able to calculate these values by hand. But in any case, you would need to have P sub u and M sub u in hand, and then you would be able to follow this procedure and figure out how to design the column cross-section. For this case, we're also going to assume that the column is inside of a building. This is a piece of information that will help us know what type of clear cover requirements we are going to have to satisfy. And lastly here, we are going to assume that our column is a square column, and we are going to assume that it has the same number of bars of steel on all four faces of the square column, and we'll see more about that as we proceed. So now we proceed to the solution, and with many things in design, we do have to make some sort of estimate at the beginning. And so what I'm calling step one here is an estimate of column size. Now, column size can be estimated by this formula here. But I want you to be careful when you use this formula, because there are circumstances where it will not give a very good estimate. So you really have to remember carefully that this is just an estimate. It is not solid. It can have some variation from the final answer, and so you of course still have to go through the design process and make sure that this estimate is appropriate. And it's also likely that you will have to make some adjustments along the way. This is just a way to get started. And so we have that the gross cross-sectional area of concrete needs to be greater than or equal to P sub u over 0.45 times F sub C prime plus Fy times 0.015. And so P sub u was 1500 kips. We plug in all of the other values here. We have F sub C prime here and F sub Y, and we get 680 inches squared. Because we assumed that our square concrete column was indeed going to be square, well then we have equal side lengths, and so then we can say that the side length is going to be equal to the square root of that gross cross-sectional area, 680, and we get 26.1 inches for the side length. Well, I am going to, with that number in hand, I'm going to round that up, and I've decided to just try 28 inches squared. There's nothing sacred about that adjustment that I made there. It's just I decided to do it. You might have chosen to use 26. I've chosen to do 28. So with a 28-inch square column as our initial guess, we next proceed to calculate what we are going to call K sub n and R sub n values. These are values that are going to be needed to use the interaction diagram charts that I have provided to you as handouts in class already. First off, we have what is called K sub n, and it is equal to P sub u over phi times F sub C prime times AG. And so then, if we put in all that information here, 1500 over 0.65 for phi, and that's the 0.65 for phi for a column in a case of axial loading. We have F sub C prime of 4 KSI, and our assumed or estimated column size is 28 inches squared, and we get there a value of 0.736. And we also need to calculate Rn, which is m sub u over phi times F sub C prime times Ag times H. And for that we have 400 kip feet times 12 to get that into kip inches. And then we have phi of 0.65. And you'll notice that in both of these, no matter what, we're using a value of 0.65. And this is appropriate for the interaction diagrams that I have provided to you. We have also here F sub C prime of 4 KSI, and then we have 28 inches cubed because we have Ag times H. And since it's a square column, that's why we have the two side lengths multiplied together times the height, which is also the same as the side length. We get 28 cubed, and we get a value here of 0.084. Now that we have these two values, 0.736 for Kn and 0.084 for Rn, we now can go to our interaction diagram chart. And so if you take a look at this interaction diagram chart, you will notice that it has an F sub C prime of 4 KSI, and it has an Fy of 60 KSI, and both of those things agree with what we had given in the initial problem statement. The other thing you will notice is that this is the special interaction diagram chart for which this variable gamma is equal to 0.8. Now, how do I know it's 0.8? Well, I don't know it's 0.8, but I'm going to, in this case, going to guess that gamma is 0.8. And gamma is basically the decimal percentage of the decimal percentage of H. And basically that means from the center of this bar to the center of this bar is gamma times H. And so we have the center to center bar distance is gamma H. Now, once we have made that choice, we come to this chart and we have 0.736 over here, and we have 0.084 down here, and where those two values intersect on the interaction diagram is right here at this red dot, and you can see that it is within or below the boundary here for gamma G, or not gamma G, but rho G equal to 0.01. Now, rho G equal to 0.01 is the smallest value of steel ratio that we can use for a reinforced concrete column. And so since this red mark is right below that, we will use this then minimum value, since we have to use the minimum value anyway. If the red mark had landed somewhere else, we would try to interpolate with our eye what that rho G value would be. So in this case, after using this interaction diagram chart, we come away from it realizing that we should use rho G of 0.01. So with gamma of 0.8, we have found rho G of 0.01. Now that we have that value of rho G of 0.01, we can find that since rho G is equal to AST over AG, we can just solve for AST, and it is equal to rho G times AG, and so that is 0.01 times 28 inches squared, and we get an AST value of 7.84 inches squared. Now, I want you to notice that if we do have equal number of bars in all four faces of our concrete column, then this for n being equal to the number of bars in each side face, we can there is a relationship for n and the total number of bars. So if we have 2 bars in each face, the total is 4. If we have 3 in each face, the total is actually 8, and so on. You can see the relationship here in this table, and that is found by this formula here. The total number of bars is equal to 4 times n minus 1. And so that's a simple formula that may be helpful to you from time to time. With that information in hand, we then can consider a variety of cases. For example, we can take this 7.84 inches squared, and we could try 12 bars, we could try 16 bars, and we could try 20 bars, and for each of these cases we could see how much then the square inches of area is per bar that is required, and then we can find some bars that satisfy those. And you can see in the first case for 12 bars we would need to have a number 8 bar, and the difference between the number 8 bar and the required area is well, there's a little bit of difference. If we try a number 7 bar, it's probably a little bit better between the difference. And lastly, we can look at 20 bars, in which case we would need to have a number 6 bar. And the difference between 0.44 and 0.39 is not so much, and so that's a pretty efficient use of our longitudinal bars. And so I am electing to use the number 6 bars here. Now that we have chosen our number 6 bars, we see we're going to use 20 number 6 bars. We can use number 3 ties, and ACI code will let us use number 3 ties for number 6 bars, so we have satisfied that. And then we can also go to the table that I have given you previously for the values of C, L, B, T, F, C, D. And for this column with number 6 bars for a column inside a building, we find that this quantity, which is the center of the bar to the face of concrete, that distance, an appropriate value there to satisfy clear cover requirements is 2.25. Knowing that value will help us calculate this distance here. And this distance here is gamma h. And we need to be able to check to see whether or not the gamma that we chose, which was 0.8, we assumed that value when we went to our interaction diagram chart, and now we need to see that that was actually achieved. And we are wanting to have 0.8 or greater. If we don't have that, we're going to have to start over and choose a chart that is different than the one we had. And so in this case now I'm going to check gamma, and so the actual gamma is going to be the total side length 28 minus 2 times this CLBTFCD. And so basically we're taking this length and then subtracting off the 2 ends, and then dividing by 28 will give us our actual gamma value. And so we can see that our bars are spaced, the center to the outermost bars is going to be greater than what we assumed. So this is actually better than what we assumed when we used that interaction diagram chart. So our column is actually going to be a little bit stronger than our design here, and so that's okay. We're erring on the side of being conservative, but yet we're also fairly close. This has worked out quite well. And so we have a design that is going to be satisfactory, it appears so far. We also need to check the clear spacing between longitudinal bars. And so we can take 28 minus that CLBTFCD value. So 28 minus 2 times 2.25 minus 5 times the bar diameter. And it is 5 because we have 1, 2, 3, 4 interior bars, and then we have a half here and a half up there, because this is to the center of bar and this is the center of bar. So we really have 5 bars, 5 bar diameters that we need to subtract out. And then we have 1, 2, 3, 4, 5 spaces, so we divide by 5 and we get 3.95 inches. And the ACI code requires that we have a clear spacing requirement of 1.5 times the bar diameter, which is 1.125 inches, or 1.5 inches. Well, the governing value is 1.5 inches, and our 3.95 spacing, clear spacing distance between bars is greater than that, so we have more than sufficient clear spacing. So we have satisfied a bunch of the spacing requirements for our column cross-section, and now we can proceed to designing the ties. Now remember that we had used number 6 bars and for the longitudinal bars, and for the ties we said we were going to use number 3s. So 16 times the diameter of the longitudinal bars is 12 inches. 48 times the diameter of the ties, which is 3/8 of an inch, is equal to 18 inches. And the third requirement, the least column dimension, is 28 inches. That's the side length of the column. Of those 3, the smallest is the one that governs, and so we have 12 inches here. That is then going to be the required tie spacing for our column. And so we're going to use number 3 ties at 12 inches on center. Now, we also need to note here that we are going to have cross ties. There are requirements in the ACI code that say that every other bar needs to have a cross tie. It needs to be either in a corner or it needs to be enclosed in some sort of hook that is holding that column in place to prevent it from lateral movement. So it provides confinement for the concrete in the interior also. And so you can see that not only do we have the number 3 stirrups going all the way around the outside of these bars, but we also have some cross ties here. And so we have satisfied all of the ACI requirements for the ties now by providing the number 3 ties at 12 inch on center in addition to the cross ties, which are number 3 also and at the same spacing. We also have the 1.5 inch clear cover that is required. We have specified our 28 inch side distance, and we also have our number 6 longitudinal bars, and we have specified that there are 20 of them. So when you do your reinforced concrete column problems, you should be providing all of this information and doing all of the spacing checks that have been illustrated in this problem. The last thing that we can do to think about this problem is look at what would happen if we had used the reinforced concrete column computer program that I have designed and prepared for you. And if you put in all of the relevant information for the column that we just designed, you would get a phi PN on the vertical axis, phi MN on the horizontal axis, and you would get this innermost interaction diagram here. And that is the interaction diagram for our column. It, however, has a maximum phi PN value here that is limited right there. But if we put in our M sub U value and our P sub U value that was provided, it ends up being right there. And you can see then that our phi PN and M sub U are within this interaction diagram and envelope, and hence our column is satisfactory. That concludes our lesson on the use of interaction diagram charts for the design of short reinforced concrete columns.